G'day everyone, welcome to lecture 4 for topic 3 of unit 3, sound resonance, which is our very last video to be recorded. And a big shout out to number 1 fan, Mr. Brewer, for always watching our videos. So this video will be covering the main ideas of chapters 15.1 and 15.2 of book 1. Please complete the reading for that before class. Alright, now here are our learning intentions and success criteria for this topic. Please pause the video and attempt to complete the KS table there over on the left. Okay, so looking at this, we can see we've got a couple of knowledge ones here. First one is, well, what is resonance? If you need to define it, you need to know what it is. Secondly, what properties do standing waves have? If we're going to calculate some properties, we need to know those. And we also need to talk about strings and pipes. We need to know what are some examples of strings and pipes. All right, now, as we mentioned back in video 3.1, sound is an example of a longitudinal wave. It's often called a mechanical or a pressure wave. And so it consists of areas of high pressure and low pressure. The movement of the energy is propagated by these alternating high and low pressure regions, and so it does require a medium to move. So in space, no one can hear you scream. And there's a fantastic movie quote there that may help you remember it. Now, according to the formula booklet, the speed of sound in air is 25 degrees Celsius is 346 meters per second. The speed does change with temperature. Now, as air temperature increases, the speed goes up by this equation. This equation is not inside your syllabus, so you don't need to remember this equation or use this equation. It could be provided to you on a question, but it's not something that you need to memorize, okay? You do need to remember that the 346 meters per second at 25 degrees Celsius is written inside the formula booklet, though. What this does mean, though, is that because it obeys the wave equation, sound is a wave, so it obeys the wave equation. So if you're talking about sound, they're going to assume that you can remember that this 346 can be substituted into this equation V equals F lambda. So in case of working out sound, you only need to know the frequency or the wavelength, because it's assumed that you'll go back to the formula booklet to get the velocity. Same sort of thing that we do with light. Now, different materials will have different speeds of sound. There's a list on page 412 in your textbook. You don't need to memorize any of them. Just be aware that if you've got to, say, comparing speed of sound in air versus speed of sound in steel, well, you would have to work out the speed of sound in steel. It would be different. If you're going to do waves as part of a IA2 experiment, then these numbers here are a handy reference. Let's have a look at an example of this. Calculate the wavelength of the musical note middle C, which has a frequency. I just need to switch over to pen. Frequency of 261.6 hertz on a day when the temperature is 25 degrees Celsius. So here we know that the frequency equals 261.6. We need to work out the wavelength. Lambda equals, I don't know. And because we're told the temperature is 25 degrees C, we could feed it into that formula, or we can use the memorized value. So the memorized value, remember, was the velocity when temperature equals 25 was 346 meters per second, I believe. Let me just double check that. Yeah, 346. So we know that the relationship between these things, V equals F lambda. 346 equals 261.6 times lambda. Lambda is going to equal 346 over 261.6. And I'll grab my calculator. 346 divided by 261.6 is about 1.32 meters. And let's see, frequency is in hertz, good. Yeah, so then there's no, that's what I'm looking for. There's no unit conversions or anything like that. Okay, on we go. Now, we saw in the first lab, the one with the slinkies, remember, how waves will reflect from boundary points. So some common examples that we will see in the syllabus are musical instruments, and they're going to be either pipes or strings. Okay, so those are the two areas that the syllabus will focus on. Resonance is a phenomenon where a wave builds on itself as energy is added at the right frequency. So this is the definition, or an abridgment of the definition from the syllabus. So when a force drives a system, so driving in this case means making it work, to oscillate with greater energy at a particular frequency. It's the particular frequency that is very important. All objects have a frequency that they resonate. It's how tuning forks work. You saw tuning forks in grade 9. Now this is a GIF I extracted from the PhET simulation, and you're going to be looking at resonance a bit this week. So we can see what's happening is that we saw the wave come in, and then we saw a sort of weird bouncing back, and now we're seeing this effect where there is very little movement very close to the green. There's a bit of, it's not a perfect simulation, so we'll get the occasional jitter around. There's very little movement around the green, and we have these areas of high movement and areas of very little movement around the green. So we've got nodes, meaning no movement around the green, and we've got antinodes, which are these two big bits oscillating upwards and downs. Okay, so this is what resonance is. It's what we call a standing wave. Okay, now the book tends to approach the instruments as either strings or pipes. Okay, so it's either made out of string or it's made out of pipe. And then it breaks the pipes down into two examples. Are they open pipes or are they closed-end pipes? And closed-end means only one closed end. I don't like thinking about it like that because there's a bit of easy, to me there's an easier way to think about it. Either the endpoints are identical or the endpoints are different. If the endpoints are identical, that means, they both might be a tied off string, they both might be an open pipe. But if they're different, then they will be two, either, in this case, the pipes will be different ending. Now, let's look at a guitar string, because this will be the foundation. If we consider a guitar string, at its simplest, it's two fixed ends with the middle vibrating up and down. Okay, sorry, I just needed to tab back to my script for that. It's kind of like a skip rope. We can see it's moving up and down. In the middle there, we have an antinode, and at each end we have our nodes. Okay. Now, if we look at the size of this wave, now remember, ignore the fact that there is a bottom and a top on this image up here. If we just look at the top, we can see that is half the wave, because it needs to go, to get back to where it started from, it still needs to go through the reverse cycle underneath it. So this wave, this half a wave, is the length of the string, or that the wavelength is equal to twice the length of the string. Okay. This, as it has one antinode, is called the first harmonic. One antinode, one harmonic. It's also the simplest shape that we can fit into it. Sometimes it's called the fundamental frequency. Now, if we draw other wave shapes in here that end with a node at each end, so ending just like with our string having one node at each end, we can fit in smaller wavelengths. So we can see here for A, that's the one that we've got up the top there. B, we can see we fit a full wavelength in, but it's the size of the wavelength is now smaller than what was before. For C, we've got 1.5 wavelengths, and again, it's smaller. These are called the modes. That's what this terminology means. That's what the terminology is for this. They are the modes of the wave, or the modes of the string. And each one is a new harmonic. So A is the first harmonic, B is the second harmonic, C is the, believe it or not, the third harmonic. Okay? Each of these harmonics is defined as a multiple of the fundamental or the lowest frequency. Whatever harmonic, it is the nth multiple of the fundamental frequency. That's what a word harmonic means. Doesn't matter whether we're talking about strings, pipes, closed or open. A harmonic, some harmonic is that multiple of the fundamental frequency. Now, if we go and do some formulas and jot down some notes here about modelling out this shape, there's this lovely little table that is inside the textbook, and we see here that the L column, the first one is a half of the wavelength, the second one is 1 wavelength, the next one is 1.5 wavelengths, and then we've rearranged whether it's L or lambda as our proceeding. Then they're substituting in for F for frequency, the names and the modes. But we can see that it's following a pattern. So 2L, 2 over 2L, 2 over 3L, and it just keeps increasing. The formula just keeps changing up. Following that pattern, we get the following formula. Okay, there it is. Now this is called the formula for strings. It's also the formula for open pipes. And so that's why I don't like to think of, is it a string or a pipe formula? To me, it's just, this is the formula when we have two identical ends, whether they're both nodes, and we'll look at open pipes in a second, or if they're both antinodes. But this is the formula for identical ends. Okay, so if we have a look at an open pipe, so this is an open pipe. I'm not sure if a flute has an open end at the bit where you blow into it. Like obviously the bit you blow into is open, but whether the length of the tube. But if we had a length of pipe, like a straw with resonance that you blow across the top of like pan pipes. You may have made one in grade 9. This is an open pipe. Now, at the end, they are not nodes anymore. They are now antinodes, because you can see here that the wave can reach all the way to the top or to the bottom. They have full opportunity to move there. We can see, though, that this simpler shape is still half a wave. In this case, it's starting at the antinode and ending at the antinode. But if we were to just look at the, you could chop it in half and rearrange it, and you would still get the same half wave shape that we saw with the string. Okay. So the length is equal to wavelength over 2. If we do the same thing as before, and we look at the different shapes that will fit into it, again, we get the same pattern appearing. So see how the first lambda is lambda equals 2L, second one lambda equals L, third one lambda equals 2/3 L, next one lambda equals 2/4 L. Again, these are the harmonics. In this case, the number of nodes, the points of node movement, the bit where the wave gets squeezed is equal to the number of modes there. So the first one, the first harmonic, n equals 1, there's 1 node in the middle. For the second one, n equals 2, there's 2 nodes. N equals 3, there's 3 nodes. And so you can see that there on the image. Another way of thinking about it is the number of half multiple wavelengths that will fit into it. So the first one can fit 1 half wavelength, the second one can fit 2 half wavelengths, or 1 wavelength, the third one can fit 3 half wavelengths. So you can see there that n equals 3, n equals 4, etc. matches up to that first number in the L column. And so we get the same equation. We get this L equals n lambda over 2. And as I said, just note that this doesn't match up the number of nodes, sorry, the number of antinodes with the mode. It's the number of nodes with the mode. So there's a slight difference there. So our last ones are closed pipes, and these are a little bit different. Okay, so at one end of a pipe is closed, which makes a node, but the other end is open, making an antinode. And so when we draw it, we get this shape happening. And so we can see here on the left, there is a node, the point where the potentiality for the wave to move is at 0. And then at the other end, the wave has full freedom to move across the mouth of the tube, and so it's open. You could kind of think of a recorder like that, because the bit that you blow in is almost pinched off. But anything that has an open at one end and a closed at the other end, actually technically a trumpet would be any of the brass instruments, I guess, because where your mouth is would be considered a node, because it's effectively solid compared to the air. Note, if you go and talk with an actual musician / physicist at the same time, they'll probably be able to give a better explanation and example. Because this now only fits a quarter of a wavelength, here's our basic relationship. And this image here has sketched out the rest of the first half of the wave. So the L equals lambda over 4 instead of lambda over 2. So there's a big difference to keep in note. Now, if we continue the pattern, drawing other shapes that start with an antinode and end with a node, we get the following pattern for waveforms. Now, there's a bit of a difference here on this one, so do take careful note of this table. And we get the formula for it as well in a second. Note the harmonic. So the first harmonic is called the first harmonic, but the second harmonic is actually the third harmonic, because the frequency is 3 times the fundamental. Then fifth and seventh. There's no even harmonics when it comes to closed pipes. It just goes up in odd numbers. Okay, so the fourth mode is the 7th harmonic. And so closed pipes do have some small complexity there, and that does have a more complicated looking formula. L equals 2n take 1 of lambda over 4. But it does use the same term. So L for length, lambda for wavelength, and N in this case is for what mode is it. You can use 1, 2, 3, 4. Just note that mode no longer matches up to the harmonic name when it comes to the closed pipe. But this formula at the front is quite useful. So here's a good recap table to keep in mind. Note the formulas in the first two formulas, the L formulas, those are the ones given to you in the textbook. The second ones with the frequencies, they are not given to you, that you can derive them by substituting V equals F lambda into them. That's all that they've done there. The third one, though, is particularly useful as a remembrance fact. So the first one is saying there that the frequency for whatever harmonic is the number of modes times the frequency, or whatever mode it is times the fundamental frequency. For closed-ended pipe, that 2n take 1, and you can remember that by seeing that you got the same term in the length formula there. If you were the fourth mode, for example, well, 2 times 4 would be equal to 8. Take 1 is 7, and so we get the seventh frequency, or the 7th harmonic. So yeah, it is a pretty useful table to keep in mind when you're preparing summary notes. Let's have a look at some examples. All right, so guitar string. So we're telling us what situation we're dealing with here. So a guitar string is 85 centimeters long, plucked in the center to produce the fundamental frequency. Plucking elsewhere may change it, not important for us. If you get a string that is plucked, unless you're told otherwise, assume it's fundamental. And the speed of the wave in the string is 420 meters per second. Note here, because we're dealing with a different material now, we're not dealing with air, because it's a string, we do need a speed given to us. For the pipes, we won't. Let's have a look. So we've got L equals 85 centimeters, so we could write that as 0.85 meters, or you could write that as 85 times 10 to the negative 2 meters. All this is converting the centimeters to scientific notation. Remember, the conversions for those are in your formula booklet. And we are told that the speed of the wave, V, equals 420 milliseconds. We're dealing with the fundamental frequency, so that means N equals 1. So first things first, we need to use our L equals N lambda over 2 formula to work out our lambda, and then we will use our V equals F lambda to take our lambda and use that, and our V, and use that to work out F, to get the frequency of the vibration. So L equals 0.85 equals 1 times lambda over 2. So lambda is going to just be 2 times 85 centimeters, so that's going to be 1.7 meters. Over here, we can go 420 equals, we're working out F, times 1.7, F equals 420 divided by 1.7 is about 247 hertz. I'll just round it off. Now, we also need to work out for part B what is the frequency of the third harmonic. So remember, because we're dealing with a string, if it was a string or an open pipe, the frequency for N equals N times the fundamental frequency, and that's what we worked out here. We just worked out the fundamental frequency. So this will be equal to 3 times 247, because we want the third harmonic. 3 times 247 is 741 hertz. Okay. So our next one here, the speed of sound waves in air at a particular temperature is 340 meters per second. I'm going to write that down. V equals 340 meters per second. Determine the fundamental frequency of a closed-end air column that has a length of 67.5 centimeters. So this here, closed-end air column. So that's talking about a pipe with a closed end. So it'll have an antinode at that end, and it'll have a node at that end. So we need a more complicated formula. So L equals 67.5 centimeters equals 0.675. Now, we're going to need to use L to work out our lambda, and then we can use with a V to work out our frequency. Same sort of approach as before. But we need the fundamental frequency, which means our N equals 1. So the formula, remember, is slightly more complicated. 2N take 1, lambda over 4. Don't forget it's 4, not 2. Obviously, it's in the formula booklet, but do keep that in mind. So let's substitute 0.675 equals 2 times 1, take 1, times lambda over 4. 2 times 1 is 2, take 1 is 1, so that's pretty straightforward. So lambda will just equal 4 times 0.675. So that is 2.7 meters. And now we can feed that into our V equals F lambda. F will equal V over lambda, 340 over 2.7. F equals 340 times 2.7, 918 hertz. Now I'm going to just include a small extension that's not given us here on the example. What if we wanted to work out the, let's see, third harmonic? Yeah, so if we wanted the third harmonic as well, okay, the F3, remember, would be equal to our 2 n take 1 times our first frequency. Now, in this case, note third harmonic means the second mode, though. So this is not the harmonic number, this is the mode number. So the third harmonic, let's just construct a small formula here. For closed-ended pipes, the harmonic number equals the mode number times 2 take 1. So if we feed, to get 3 over here, we're going to need 2 and take 1. So add 1 to both sides. That's going to be 4 equals 2n, n equals 2. So we would need to feed 2 into here to get this. And so then we'd end up with, still would end up with a 3 there, and then 3 times that to get our frequency. What we wouldn't want to do is put 3 into here, because 2 times 3 take 1 would give us 5. That'd be the 5th harmonic. So you just got to remember that this 2n take 1 is for the mode. If you want the harmonic, okay, well, we could just use the 3 times it straight away, so that's nice and easy. Just keep in mind mode versus harmonic. Last example, an open air pipe. The speed of sound waves in air at 25 degrees Celsius is 346. V equals 346. In experiment, students want to make an open-ended pipe that has a fundamental frequency for the musical note C3, which is F equals 130.8 Hertz. Determine the length, and we want fundamental frequency, so n equals 1. So this one is, we're going to go the opposite way. We need to use our first two to work out wavelength, then we can use wavelength to work out L. So V equals F lambda, lambda equals V over F, 346 divided by 130.8. 346 divided by 130.8 gives us a wavelength of let's round that up to 65 meters. And now, because this is an open pipe, so we can see here it's an open-ended pipe, length is going to equal n lambda over 2. N equals 1, so it's nice and easy. N equals 1 times 2.65 over 2 equals 1.325 meters. So about 1.33 meters. Okay. Alrighty. So that brings us to the end of this video. So in this video, we have looked at the following. Firstly, the speed of sound and how temperature affects it. We've done a brief introduction to resonance, and we've looked at the relationship between length and wavelength for instruments and the concept of harmonics. For your entrance slip to class, please complete questions 1 to 5 in chapter 15.1 and questions 1 to 9 in chapter 15.2. Copy your answers for those into the 3.3.4 space on eLearn. Remember that it is in book 1, not book 2. Thank you very much for your time. Have a great evening.